Hello and good morning, dear students. Today we are going to study next point on chapter 3, which is partial derivative of a vector. So for that you already studied what is mean by partial derivatives of a function. Okay? So for that you have studied partial derivative of a scalar function. In partial derivative of a scalar function, suppose that scalar function is a function of two or more variables, more than one variable, and if we take derivative, suppose this is a scalar function which is function of three variables x, y, and z. If you take increment out of these three variables in only one variable, okay, then you can say x changes by x plus delta x, where delta x infinitesimal increment in this, okay, x. In that case the derivative of phi with respect to x is known as partial derivative of that scalar function. Now we have to find out or see similar definition. Instead of scalar function we have to take vector function. Okay, suppose vector v is the vector function which is function of x, y, and z. Okay, so here again we have more than one variables, 2, 3, 4, 5, etc. These are the variables of which this vector field function is a function. Now here if I take infinitesimal increment in any of these three values, any of these three variables, suppose we take increment in x which is delta x, then such function is known as v, which is function of, which is again a vector function which is function of x plus delta x, y, and z. Now for definition of partial derivative, here we have to take subtraction of these two functions, which is v, which is function of x plus delta x, y, and z, minus v, which is function of x, y, and z divided by delta x. Okay, if you take limit as delta x tends to 0, this is the definition of partial derivative of this vector function with respect to x. Okay, this definition is similar for scalar functions. Instead of scalar, here we have only vector function, vector valued function. Okay, now in this partial derivative, if you take partial derivative of v with respect to y, okay, now our definition will modify as limit as delta y tends to 0, and instead of x plus delta x, here we have y plus delta y. Okay, and here we have delta y. So limit as delta y tends to 0, v of x, y plus delta y, and z, this is function of these variables, minus v, which is function of x, y, z divided by delta y. So in this way we can find out partial derivative of v with respect to y. Now on the similar way you can find out partial derivative of v with respect to z. So in that case, limit as delta z tends to 0, v, which is function of x, y, and z plus delta z, minus v, which is function of x, y, z divided by delta z. So in this way we can define partial derivative of v with respect to z. Okay, so here after this, finding out partial derivative of any scalar function, we can define partial derivative of v with respect to x, v with respect to y, okay, and v with respect to z. Now with this basics we are going to move on next point, which is vector differential operator and Laplacian operator. and Laplacian operator. So to study what is mean by vector differential operator and what is mean by Laplacian operator, we have to take a field which is scalar field, and that field is defined as phi, which is function of x, y and z. So phi is the scalar field. Before this section we have studied partial derivative of vector. Okay, now here this phi is a scalar field. Okay, so this is a scalar field. Now if you take total differentiation, okay, so total differentiation of phi is defined as d phi. So by taking total differentiation, so by definition of total differentiation we know that here all the three variables are going to increase by infinitesimal amount, which means x is going to increase by delta x plus delta x, y is going to increase by y plus delta y, and z is going to increase by z plus delta z. And d phi means what? After increasing all these three variables, what are the increments? What is the increment in the function? Okay, so that is mean by total differentiation. You already studied how to find out total differentiation of a function. So here d phi is defined as partial derivative of phi with respect to x into dx plus partial derivative of phi with respect to y dy plus partial derivative of phi with respect to z into dz. Now you can write this term, okay, which is on the right hand side, as dot product of two vectors. What are those two vectors? See over here, this is dabba by dabba x I cap, okay, plus j cap dabba by dabba y plus k cap dabba by dabba z multiply by phi. Okay, so this is the first term of dot product. If you take dot product of this term with dx I cap, dy j cap and dz k cap, in this case dot product of these two terms is nothing but coefficient of I cap is dx over here, and here dabba phi by dabba x over here. So dabba phi by dabba x dx plus dabba phi by dabba y dy and dabba phi by dabba z dz. So here we get this term. Okay, now we can write this term as we can write this term as gradient of phi, and this term dx I cap as vector dr. Now here we get definition of vector differential operator. So vector differential operator is this, which is denoted by this symbol, which is known as del or nebula. Okay, so we call this symbol as del or nebula. Okay, we are preferring del. Okay, so vector differential operator del is the again vector operator, which is defined as del as I cap dabba by dabba x plus j cap dabba by dabba y plus k cap dabba by dabba z. Okay, so this is the operator. Okay, operator means what? When we operate this del operator on another function, it produces totally different function. What is it means? Suppose you operate del operator on this function phi. So if you operate this del on phi, you will get dabba phi by dabba x I cap, dabba phi by dabba y j cap, dabba phi by dabba z k cap, which is different than phi. Okay, so in this way we are calling this term or del operator del as operator. Okay, so remember this definition of vector differential operator. Okay, now we are going to study Laplacian operator. Now this this differential operator is a vector quantity. See, we get components of I cap, j cap, and k cap in this del operator. Now Laplacian operator is a scalar operator. So to find out what is the Laplacian operator, we have to take, suppose we have del dotted with, suppose you take del, which is this operator, dotted with gradient of phi. Okay, or del dotted with del. In that case, what we will get, this is equal to, on the right hand side, del operator is what? This operator I cap dabba by dabba x plus j cap dabba by dabba y plus k cap dabba by dabba z. Suppose you take dot product with gradient of phi. Gradient of phi is what? Dabba phi by dabba x I cap plus dabba phi by dabba y j cap plus dabba phi by dabba z k cap. If you take dot product, what we will get? See, coefficient of I cap is dabba by dabba x, and here coefficient of I cap is dabba phi by dabba x. So multiplication of these two terms is del square, which is second order partial derivative of this phi with respect to x. Similarly, if you take j cap coefficients, so that will become second order partial derivative of phi with respect to y and second order partial derivative of phi with respect to z. If you take phi common from all this, so this is nothing but we are calling this as Laplacian operator, which is del square. Okay, so see, definition of Laplacian operator is what? If you take del square, which is dabba square by dabba x square plus dabba square by dabba y square plus dabba square by dabba z square. So this is the definition of Laplacian operator. Okay, now see, in this Laplacian operator, as I as I told you, this is a scalar operator because here we don't have any I cap, j cap, k cap coefficients. In vector differential operator, we have those coefficients I cap, j cap, and k cap. That's why this is a scalar operator and that is a vector operator. Okay. Now, this vector differential operator and Laplacian operator, that point is finished. Now, in physics, we get, or we have this Laplacian operator in many equations. Okay, in physics we know that in physics laws, different laws are in the form of equations. Okay, and those equations are partial differential equations. You must have studied ordinary differential equations in which we have differentiation, total differentiation, and only one independent variable is there. But in physics, in most of the cases, we also have partial differential equation in which the function the function is not function of only one variable, which is function of more than one variables. So in that case, we have partial differential equations. So what are those equations which appear in physics and this Laplacian operator appears in physics? First one is wave equation. In physics, wave equation is like this: del square psi is equal to 1 upon c square dabba square psi by dabba t square. So here we have this Laplacian operator. Psi is the, we oftenly called that term as a wave equation or wave function. Okay. Now next we have Schrodinger equation. Waves are anywhere. We know that light is electromagnetic wave. Sound waves are there. So all those waves are expressed in the form of these equations. Now next is Schrodinger equation. In Schrodinger equation, which appears in quantum mechanics, okay, so again Schrodinger equation is a wave equation which is in the form of, for wave function of that particle, I capital H is the Hamiltonian, dabba psi by dabba t is equal to minus h cross by twice m del square psi, okay, plus v of psi. Here del square is again Laplacian operator. So Schrodinger equation is the equation which tells us about conservation of energy in quantum mechanics. So this is the total energy, this is kinetic energy, this is potential energy term. Now next, Laplace equation. In physics, we oftenly encounter with Laplacian equation, which is del square psi is equal to 0. So Laplacian of this function is equal to 0. Again, Poisson's equation. This Poisson's equation appears for charge distributions. Okay, so which is in electromagnetism, you oftenly encounter this type of equations. Del square psi is equal to minus rho upon epsilon naught. You know that rho is volume charge density, epsilon naught is the permittivity of free space. So here in physics there are many more relations in which we have these operators, Laplacian operator as well as that vector differential operator. Okay, so with this we finish our lecture over here.